I'm wondering if any of you have noticed that there might be another answer, actually, for all of these. And what would that answer look like? I corrected myself once when I said this isn't the antiderivative, it's an antiderivative. There's another antiderivative. What would it be? Or what can it be? Think about that. Well, the answer would be anything of the form x squared plus x plus a constant, because the derivative of a constant is 0, and that doesn't show up here. So there's no way to tell if the constant might have been 0. The constant 0 would give you the same thing, or 2, or 10, or pi. Really, any constant would work there. So all of these, if we put a plus c at the end, so on and so forth, those would be the general antiderivative of this function. X squared plus x plus c is the general antiderivative of 2x plus 1. X squared plus x is a specific antiderivative of 2x plus 1. C is obviously called a constant. Next, we're just going to work with some symbols. Get this down symbolically. There can be, just like derivatives, there's so many different ways to say derivatives. There's a couple different ways to say antiderivatives too. It'll take us the rest of the semester probably to figure that out. So, go back to our first one. Suppose a function is 2x. The general antiderivative, and we use, generally for a function, we use a small f for the function and a big F for its antiderivative. So the general antiderivative here would be x squared plus c. Can be confusing. Big thing here. Know that if you're seeing a big F, usually means antiderivative. Next idea here is something called a differential equation. And there's a whole course, a calculus course in college that engineer types usually take, and math majors obviously, and a lot of other fields on differential equations. We're going to start that idea right now. A differential equation in x and y contains some x's, some y's, and some derivatives of y. We'll work more in depth with these throughout the semester, and some specifically interesting ones. But today we're solving ones where the derivative is isolated. So for example, suppose we have that differential equation. The derivative equals 2. We're looking for, this isn't a 1, sorry, apostrophe. We're looking for the antiderivative then to solve this differential equation. That's usually what you want to do with the differential equations if possible, is to solve them. So we don't want the derivative of y, we want y. So what would y equal? Hopefully you're thinking 2x. The derivative of 2x is 2, but I want to be general plus a constant. So another way to think of this, think of it graphically. We have the slope is 2 What satisfies that? A line with slope 2, but the y-intercept can vary. So there's many different solutions. To say it's just 2x, well, that's one specific one out of an infinitude of options. Working with notation still. You may have seen a new symbol as you look ahead in the book in chapter, usually in a calc book, it's chapter 4 and on. And we're going to show you what that symbol means right now. Suppose you have the derivative dy dx equals some function. We can get an alternate form of that by multiplying both sides by dx. And this really means derivative y. So you want to think of that. How do you undo derivative of y? You do an antiderivative. So on the left side, let's take antiderivative, we get y. And on the right side, here's the new notation. It's that symbol. I don't know its name, but this is a general form for an antiderivative. It's also called indefinite integration. Antidifferentiation, indefinite integration. This part right here has a special name. It's called the integrand. The function that you're going to take the antiderivative of. This part right here, that is the variable of integration. So once again, two names, integral or antiderivative. We'll use those interchangeably this semester. Now it's time to build up some basic rules. Some of them we already introduced or we worked around with in the first dozen or so examples that we did today. Title of this table will be Basic Integration Rules. Remember, integration, same as an antiderivative for us today. So first one, we're going to take the antiderivative of a derivative. Hopefully you're thinking, well, that just gives us the function back again. In other words, this derivative is canceled by the antiderivative. And we do need to add our plus a constant in there. So this already brings up the question, our differentiation and antidifferentiation, derivatives and integrals, are they inverse operations? No, that's not what I'm saying. Are they commutative? I think that's what I want to say. If you apply one, then the other, does it exactly give you back the other one? Not exactly, because of the plus c. Inverse operations is what I want to say. Not exactly, but almost. Let's continue. Just like derivatives, we have the same rules. So say we have a constant, we'll call it k, times a function. It would be really nice if we could ignore that constant, if we'd like to, and we can. So we can pull the constant out, do the integral. So that's going to be called the constant multiple rule. Next one's already been alluded to. Suppose we have the integral, indefinite integral, of the sum of two functions. Think polynomial. It would be really nice if we could take the indefinite integral of the first one and add it or subtract it. If this was a subtraction, this would be subtraction 2 to the other one. And that is good news, exactly the way it works. Along the lines of the first one, I forgot to say this, let's do it the other way around. Let's take the derivative of the integral, and because I'm differentiating, I'll get a constant for this one, a plus c, but the derivative of that plus c would just be 0. You do get the function back again. So this way, they're the same thing, here and here, but this way, they're different by a constant. Let's use these basic integration rules. We might need to